The first gas turbine problem we are going to solve is a simple Brayton cycle problem. So let's go to chapter 8 in the problems module, and let's go ahead and solve problem 8-1-1. We'll copy this problem to the PowerPoint and continue from there. So I've copied the problem here. So let's look at the problem. What is given here is that air is entering the, this is an air standard Brayton cycle. Air is entering at kind of atmospheric condition, 100 kPa, 25 degrees Celsius. And the volumetric flow rate is given. In other words, the mass flow rate is not given, and we know how to convert volumetric flow rate into mass flow rate. The compressor pressure ratio is 12. So if this is 100 kPa here, it will be 1200 kPa at state 2. So it will be 100 kPa here, 1200 kPa, 1200 kPa, back to 100 kPa. And the turbine inlet temperature is 1100 degrees Celsius, right? Okay, so these are some of the data given to us. Even without looking at what do they want us to find, our goal should be to clearly to find state 1, 2, 3, and 4, and then analyze each of the devices, and then try to answer the question. If we know network, heat in, we can find thermal efficiency. Net power output would be W dot T minus W dot C, and the back work ratio is essentially is considered what is the turbine power divided by the compressor power. So I hope you can study the book to some of the definitions that I haven't covered in the lecture. You can go back to the book and read up about that. Okay, so let's get started. The first step, as usual, will be to draw a TS diagram of the ideal Brayton cycle, which we have done a number of times already. Okay, so let's start with the compressor analysis. For that, we need to know state 1, 2, 3, 4. State 1 and 2. So let's write down what you know about state 1. Pressure is given as 100 kPa. And temperature is 25 degrees Celsius. So let's convert temperature to Kelvin. Is 273 plus 25 would be 298 Kelvin. The volume flow rate is given. The volumetric flow rate means what is entering at state 1. So V dot 1 is given to us to be 8 meter cube per second. So what is the mass flow rate? M dot density times volume flow rate. And what is density? Inverse over specific volume, right? Using the ideal gas equation of state, PV equals RT, we get V equals RT over P. So the mass flow rate becomes the value for R for air, this should be the value for R, value for CP, and value for K should be familiar to everybody. K is 1.4, CP is about 1.005, and R is 287. Where do you find these values? Of course, you go to the tables module property tables, and the PG model, common gases, and air should be the first one. You'll find the value of R, Cp, Cv, K right here. Okay, so now that m dot can be evaluated, if you substitute the values, V1 is given as 8, pressure is 100 kPa, R is 0.287, and temperature is 298. If you do the calculation, that comes to 9.35 kg per meter cube. Now let's go to state 2. What is known about state 2? Notice that entropy remains constant, so we can write pressure is, I think the pressure ratio was 12, so it's 12 times 100, 1200 kPa, and entropy at 2 equals entropy at 1. So how can we find temperature? Because we need the temperature to find the compressor work. If the process is isentropic, we can go back to our formula sheet, which is where I believe on this tab, and you notice that if entropy remains constant, we have constant entropy formula for the PG model, and this is equation 11 is a very important equation. You notice that we know the pressure ratio, so P2 over P1 is known, so this part T2 over T1 and P2 over P1 are connected by this equation, equation 11. So we go back using once again, T2 over T1 is P2 over P1 to the K minus 1 over K. So substituting, we get T2 equals T1 is what? 298 Kelvin. And P2 over P1 is 12. 1.4 minus 1, 1.4. And if you do the calculations, it comes about 606 Kelvin. So what will be the compressor work? Compressor work will be, if you recall, m dot Cp T2 minus T1, and we have found m dot. Cp is known, 9.35. Oopsie. Okay, so if we substitute the value 9.35, 1.005, 606, 298, and the compressor works turns out to be 2895 kilowatt. Okay, let's move on. The next step is what? Finding state 3, which is okay, for state 3, we know it's a constant pressure heat addition, so therefore P3 equals P2 is 1200 kPa, And what else is given to us? The turbine inlet temperature must be T3 is 1100 degrees Celsius. Add 273 to that. Oops. Okay. The PowerPoint crashed, so I just restarted. So let's go back to state 3. We already know pressure doesn't change during heat addition. And the temperature is given as turbine inlet temperature So we already know pressure and temperature, so state 3 is solved. Therefore, so what is going on between 2 and 3? This is the heat exchanger, you can think, from 2 to 3, and we're adding heat here. And Q dot in is m dot, the higher of the two, H3 minus H2, m dot Cp. M dot is 9 point, what did you calculate m dot to be? I wrote it down somewhere, 9.35. Cp is 1.005. T3 is 1373. And T2, we calculated T2 already, 606. Oops, lost the pen again. And Q dot in turns out to be 7206. So the final device or final state also is state 4. So recall that's the turbine exit state. So P4 is P1, and entropy we know at S4 and S3 are constant. So this is our turbine from 3 to 4, isentropic turbine. We know all about state 3 and we need to find T4. Again, if you use our isentropic relationship, we know that we can write T4 or T3 over T4, the isentropic, equal P3 over P4 to the K minus 1 over K. The isentropic formula, again, we used it for compressor also, equation 11 from the formula sheet. So therefore T4 will be T3 divided by 12 to the K minus 1 over K. T3 is 1373. Solving, we get a T4 of 675 Kelvin. That's quite hot. That's the turbine exhaust, which is really thrown out. If we want to find the turbine work, which will be m dot Cp T3 minus T4, 9.35, 1.005, T3 is 1373, 675, and that is 6558. And because now we know all the states, we can find the Q dot out. Q dot out can be calculated m dot, which is bigger, 4 is bigger, right, than 1. So you can intuitively write the formula. The amount of heat that is coming out of the heat exchanger, 4 is where it's entering, the air is entering, 1 air is coming out at 1, and heat is rejected. So you can see that m dot h4 is what? How much energy is entering, transported by this mass, and m dot h1 is how much energy is coming out. The difference must be what must be coming out as Q dot out, heat transfer, because there is no other energy transfer in this heat exchanger. So substituting the numbers we already got, mass flow rate, Cp, and T4 was what? 675 minus T1, which is 298, and that should be about 3543. Now that we know every device, we have analyzed every device, what are the questions? The first question is find the thermal efficiency. So what is the network? To find the thermal efficiency, the easiest way is to find the network. We have found compressor work, turbine work. If we substitute the two, 6558 minus 2895 approximately here, and that is equal to 3663. We have also found, so this is, I think this is one of the questions to find. I think one of the questions is that find the net power output. So this is part of the answer for part B. Let me create another slide. Probably this is the last slide for this problem. So what is thermal efficiency? If you recall, thermal efficiency is W dot net by Q dot in. You could write that as, W dot net and Q dot net are the same in any cycle like this, and Q dot net is Q dot in minus Q dot out and Q dot in. So you can use any of these formulas, but in this case we already know W dot net, which is we just calculated it. How much? 3663. And Q dot in is how much? I believe we did that a couple of slides ago. W dot compressor, Q dot in was 7206. So the efficiency is right about, let's do the division, and it turns out to be 50.8%. Instead of fraction, it's a standard practice to express that in percent. And what is back work ratio? Back work ratio is the amount of work that is consumed back. The turbine produces so much more than the compressor. So it tells you that how much of the work produced by the turbine is eaten up by the compressor. The turbine work we calculated as, okay, this is compressor work 2895. And what is the turbine work? Q in 6558. So that's 0.44 or 44%.